Now is where I actually try to observe traffic, and hence I try to convert what I normally observe when I'm moving in vehicles and somebody is driving and I'm doing nothing but thinking into observation in terms of these three fundamental quantities. So let's plot a nice graph between these three fundamental quantity, and remember that this comes from actually observing in an observation window. So the first one is I try to plot in the density versus the average speed. I try to plot the density versus average speed, and this is purely by observation. So what really happens is when the density is very low, you tend to drive at more or less the maximum speeds possible. So that's as per your transportation department, what is the maximum speed possible. So you travel with the maximum speed possible for low density, but as vehicles come in, what really happens is that you start getting more conscious. So you're more conscious that I shouldn't just dash with the person in front, or the time gap is reducing and the space gap is reducing because the same road has more number of vehicles. So you're just a little bit conscious, so you lower down your speed, you lower down your speed, you lower down your speed, you lower down your speed. Now what really happens is that this is what is called as a congestion. This is what's a traffic jam. So at congestion, what happens? The traffic density is so large. The traffic density is so large. The traffic density is so large that nobody is moving. And nobody can really move because in order for you to move, you need a specific space gap, at least some certain space gap, some certain time gap from the vehicle in front. And you're not getting that space gap because the density is so large. So you just keep on waiting. Your speed is zero because you don't have enough distance from the vehicle in front. So you cannot move because of the vehicle in front. The vehicle in front cannot move because of the vehicle in front. And nobody in the vehicle in front can move. So that's what's a traffic jam. That is what is a congestion. Nobody moves, and that's what we observe in traffic. That everybody is stuck. Nobody is moving, except for probably the first few vehicles at an intersection. But that assumes that there's an intersection and a red light or something is the one that's causing a traffic jam. Otherwise, if it's a highway, everybody's waiting. Nobody's getting that space gap, so everybody's waiting at zero speed, and that's what's a congestion. And that's exactly what is one of the reason why transportation systems, they actually perform badly at times. The transportation system performs badly at these times. Now, if you are looking at this curve, you will say that okay, everybody need to drive at 60 kilometer per hour, 100 kilometer per hour, or whatever maximum is allowed. Lower speed is okay, probably 40 kilometer per hour is good enough for driving. But then, if you are not getting enough speeds, the worst thing you can do is to increase the density. Now, do I have a control on the density in real traffic? No. Somebody wants to go out of the home at 5 p.m., that person will go out of the home at 5 p.m. That person is not going to wait. That person is not going to look at the speeds and say, okay, maybe I don't go out and control the density. Me going out will be extremely bad for the traffic. The speeds will reduce. That person will still go out. And because that person will still go out, the density is going to increase and the speed is going to reduce. So the problem with the traffic is that we really cannot control the density. People who want to go out will go out. There are some things that you can do. You can suggest alternative routes. Currently, we haven't taken more number of roads. So you just suggest people that avoid these roads and do this. That's all some part of the problem in reducing the density. But if you cannot control the density, then the speeds ought to be very low. And that's exactly what happens, especially in our city, where there are not many alternate routes which are available, and the people who want to go out absolutely don't care and they have to move out. So, what? My suggestion is, of course, there are places where there are congestion tax. So if the speed which you are monitoring is at a critical level and still people go out, they are taxed. Or you know at what speeds the density becomes very large, so those people are taxed excessively. You go out, except for public transport, so you go out at the wrong time and there is all the congestion, you pay a higher tax. This is of course the first fundamental diagram, currently from observation. There's another way you can study it up. Let me take in another. So that's my density and that's my flow. So flow is number of vehicles passing per unit time and density is number of vehicles per unit space. So what really happens is when density is extremely low, so there are hardly vehicles. And because there are very few vehicles, the number of vehicles per unit time is also going to be extremely small. So this is what happens. So when there are no vehicles, then the flow is of course zero. As the density increases, you at least get vehicles to travel and the flow increases. And more density increases, the flow increases until it reaches a peak. After that, suddenly it starts to reduce, and that's from observation, and it goes like this thing around over here. So this is what is called as an underflow. So all vehicles at this region are mostly going at their maximum allowable speed. They don't care about each other. There's hardly any density. Mostly vehicles are free flowing. They're going by their natural speed. So it's also called as a free flow. However, the flow is small because the vehicles are not there. So very few vehicles are moving. So the person observing is not getting vehicles to count. This is what is congestion. So there are too many vehicles, but they are all static. They are all at rest. Nobody is moving. So the person observing is counting vehicles that pass by. The vehicles are not passing by. They are just standing still. So the flow is zero. And this is what is called as a capacited flow. Now, we discussed making roads, whether flyovers should be built or not, and everything. And this is one very important metric that exists for the transportation engineer. So if you are a transportation engineer, flow is your metric. So you know that we all subscribe to internet services and people try to maximize the bandwidth, which is the amount of data that flows, to manage networks such that maximum amount of data flows. That's the utility of the transportation network. Now, a transportation engineer will never try to maximize the speeds by which the vehicles move, because there's only one vehicle at the road, the speed is maximum, but the transportation infrastructure is poorly utilized, it is underutilized, which is this region. There are only few vehicles, they are moving at great speed, but the transportation network is underutilized. It's like for one person you build an entire flyover, we haven't taken multiple lanes, but you build up a very wide road for just one user. So the transportation network is poorly utilized. Everybody is going by the maximum speed, but your multiple crawls are being used by just a handful of people. You could have better told them that even if I don't provide you this world-class infrastructure, you'll still have a great transportation experience. So why do I spend crores for you? On the other hand, if there's congestion, which is this region around over here, it's also very bad. So congestion is obviously extremely bad because nobody's moving. So you've got a high demand, nobody's moving. So your aim is, as a transportation engineer, to get into this region. All your aim as a transportation engineer is to operate over here, or to increase this much as possible. So there are enough users, people are using it. So the number of vehicles per unit time, it's same as increasing internet bandwidth. So there are enough users and they are having high speed. So you want to increase the capacited flow. Now, an easy way to say that is, how do you do that to control the density? So for every segment of the road, we are only looking at one lane and one road right now. You have to control the density. You are lucky if this is a road that does not have residential complexes, because then nobody will enter the road and nobody will exit the road other than the known entry exit points which are controlled by traffic light. So if there are too many people and if your density is high, then you can always tell the previous traffic light to go red. So this is the, in terms of space, the road that I'm considering. And there's a traffic light over here and there is a traffic light over here. So if the density is extremely high, you can make this as red, and if the density is extremely low, then you can make this as green. So controlling this, you can control this part of the network, but the problem is when there are people around. So these are homes. The problem is when there are people around, and when there are people around, then you cannot control it. People will come out as and when they like. There's actually a bigger problem that to control the traffic density over here, if it's getting extremely dense, then you can always say that this is becoming red. But then if this becomes red, there's another road which is over here, and the vehicles cannot move out and the vehicles come in. So it causes a congestion here. So to control this congestion, I've got it cause a congestion here. Worse still, that it may have multiple entry points. So it's a tough problem. It's a tough problem about how do I control the density so that I strictly operate at my capacited flow. Now, seriously speaking, density is again not in front of your hand, not in your hands. The people who have to move out will move out. The maximum you can do is to plead them. So the best way out is to have roads which have multiple lanes. So once your multiple lanes increases, then you're virtually adding roads. And if you're adding roads, then of course the transportation will become more efficient. But then of course that costs crores of rupees. Otherwise, what? You have to control the density, increase the toll tax, people will not be able to enter, ban vehicles only public transportation, which is the best solution of course, or increase the taxes so that lesser people can afford vehicles that go into these kinds of roads. That's actually bad. Or make some roads which are prime and then control the traffic lights such that not many people enter into those roads. The problem is, how do you control the density? The easiest way is to increase the infrastructure, but then of course that costs quite a lot. The other is of course to maintain this kind of a trade-off. If you can really increase the density by some other way. There is, of course, I plotted, there were three variables: speed, density and flow. So there will be 3C2 graphs. So there are two, so there's another one, and I need not draw that up because the two are controlled by a fundamental equation. So let me just plot the third one as a formality. The fundamental equation, flow, is density times the speed remains. So the third one will be between average speed and a flow, and obviously the same thing will happen, that when the flow is small, it can be either because of an underflow, in which case the speeds are very large, or it can be because of a congestion. The speeds are very small, but then the flow is zero, of course, and that's how it will go. So this is just using, and this is the capacited flow. So the flow is at the maximum, and the speeds are average because the density was increased and the speeds was reduced. Otherwise, a zero flow was given. High speed was zero flow when the vehicles are traveling at great speed, but there are not many people using the vehicle. So this one is directly from the fundamental equation, where this is of course a congestion. This is the capacited flow, maximum flow, and this one is a underflow or a free flow. Here also I need to get into this region. Here also I absolutely need to get into this region. That is what is my aim. Of course I cannot control the average speed. The people will not be able to drive at a higher or a lower speed. They will only drive at speeds which are permissible as per the current operating of the traffic density. So that's not something which is in my hand. And these are the three called as the fundamental diagrams. So these are the three fundamental diagrams which currently drawn by observation. It enables us to understand as to what really does happen. Why do traffic congestion happens? Why is everybody moving? Why is everybody not moving in a congestion? Because everybody is waiting for a space gap, and the space gap is absolutely not coming, and because the space gap is not absolutely coming, everybody is just waiting for it. So any traffic simulation system, so far we just simulated it up based on our understanding. Now we'll need to, because these have come from actual observation, so we will have to ensure that these kind of an observation are what are adhered to, what are replicated by any simulation system. So, briefly touching upon, if we need to understand it, let's understand a kinematic wave. And I take in a simple scenario, there's one road, one lane, and there is a traffic light over here. And because there is a traffic light over here, let us say that it turns red. Now, the moment it turns red, in any traffic, there's an outflow and there is an inflow. So in any such kind of a road, there will be an outflow and there will be an inflow. The inflow is the rate at which the vehicles come in, summation of all these inflows. So I'll take this inflow, this inflow, this inflow, which is the vehicles per unit time. So it's flow, it's vehicles per unit time that come in, and similarly the vehicles per time that go out. Now if your outflow becomes smaller than inflow, which is exactly what happens in red light, the outflow becomes zero and the inflow is still positive. And when your outflow is less than inflow, then the effect is what is a queuing. And the rate of queuing is of course the inflow minus the outflow. So the rate of queuing is the inflow minus the outflow. And you'll see a queuing which will happen, and you know that the outflow is of course zero in this case. You know the inflow from the flow network information, so you know the rate at which the vehicles are moving. Now what's happening over here is that you'll see the vehicles will travel mostly by their nominated speed, and they'll start queuing up over here, and that's how queuing will happen. So these vehicles will be nicely traveling, and suddenly they'll start queue and then they shall stop over here. Now this is said that there's a kinematic wave which flows like this, and this one is also specifically called as a shock wave. So the shock wave is the wave which goes on like this, and it sends a shock, so everybody is stopping. So everybody is absolutely stopping over here, and that's what you see is a shock wave that goes backward into the traffic. Let's discuss in the other one as well. So let's say that there's a road over here, and suddenly that after here, what happened was that there was some queuing that already happened, and now the light turns green. So don't see the color, it's green. Now the traffic starts to move, and now when you see the traffic starts to move, you see that there's a go wave which will go around and the vehicle will suddenly start moving. That's not the only case when the shock wave will go. Now imagine something which is very common. So there is a nice road like this, there's an absolutely nice road, and unfortunately what happens after the nice road is there is a bad road. And you know, at this road, what happens? You'll have to slow down. So vehicles are coming at very high speed over here and they are slowing down over here. So that's another thing that sends a shock wave over here. And that's why what you will see in both these conditions, a very obvious observation in both of these conditions is that you will see the vehicles keep slowing down much before. So over here what will actually happen is in both these situations, here you will see that these drivers, they tend to slow down a lot before because they know that this shockwave needs to happen. And because the shockwave needs to happen, they slow down and they smoothen the effect of the shockwave. Similarly over here you see the people slowing down much before. In this case, slowing down much before is much better because imagine what happens in green light if you don't slow down much in advance. So this is one situation and this is the other situation. So when the light turns green over here and when the light turns green over here, what really happens is that in the first situation the space gap is small and the wave slowly goes around here, and here the space gap is already large, so the wave travels much smaller. So in traffic light you see that's why people intentionally tend to keep an enough gap. Now that's again not a very good strategy because the roads have just small bandwidth. So if everybody starts keeping a lot of distance from the vehicle behind, all the vehicles will not fit in the physical road, and the space utilization is going to be another immense problem. So keeping too much of gap is obviously not the solution, but then you see that when the light turns green, the vehicles in the second scenario already have an enough space gap, and because they already have enough space gap, the wave will travel much faster than it will travel around over here. Sometimes what really happens is that you've got in waves called as the stop and go waves. So you stop, you go, you stop, you go, you stop, you go. So it's an amalgamation of a stop wave and a go wave, and both the waves they travel at different. Both the waves travel at different speeds, depending upon the situation which is causing that up, and both merge, they intersect, they cancel each other out, and all that things happen. So it's a normal wave. So it will have everything to do with a normal wave, and that's exactly what the effect is gonna be like any normal wave. So these are all the kinematic waves, so that it enables us to really understand what's happening out there in traffic. So again, a quick scenario will be, I take in a normal intersection. Now of course the outflow here is inflow here plus inflow here, but then the capacited flow over here is a threshold, the capacited flow over here is a threshold, and the capacited flow over here is the same threshold because they're all one lanes. Now what will happen around over here is, because this kind of a merger is happening, I don't have the bandwidth to accommodate both the summation of inflow, so that means a slowing down will happen, or a slowing down will propagate around over here, and that's exactly what you see many times in highway. When you want to enter into the city, then different roads are merging into one, and because different roads are merging into one, there's a natural slowing down behavior that you really need to show. The opposite is the case of a diversion. So in case of a diversion, exactly the opposite happens. So there's small flow over here. However, the flow gets divided into two. So this flow is this flow plus this flow. This flow is having a small capacity and the same is over here. So there's no way that congestion can build up around over here. And there's no way that congestion can build up around over here. So there's a slowing down wave in this case. But here what happens is that the speeds start to increase because of my increase of the bandwidth, and because of an increase of the bandwidth you suddenly start going a lot faster. And that's exactly what happens the moment you go into an intersection. A lot of people are leaving the city and there are different ways, so they all diverge. And then once you're into the highway, you can go at absolutely very fast speed because of this thing. So, I mean, that's just to give in a little bit of a flow, and that's just to give in a little bit of a flavor about how macroscopic simulation works. So all that I did was I took a macroscopic window, I observed it up, I plotted this thing, I did some reasoning, and then we looked at more or less like the particle nature of things, where there was a density, there was a flow information. We tried to say how does it interact with each other in case of intersection, diversion, traffic light, what kind of waves will follow, how will the waves intersect, merge, what speeds will the waves move. So that's all how we analyze a traffic system or a traffic management from a macroscopic point of view, looking at different conditions, commonly occurring conditions, traffic jams or accidents or something like that, and what kinematic wave does it produce, how does it propagate, and what's the effect on different macroscopic variables along with time, along with space. That's how the macroscopic simulations are studied, and that's how microscopic simulations are beneficial to analyze a lot of vehicles. Remember, each one of vehicles wasn't particularly simulated. That's how I analyze a lot of things around using basic kinematics equation, using basic flow equation, using basic equations that was otherwise associated with all the water bodies flowing and all the currents flowing and all. And that's exactly how we have modeled the traffic system, and we try to give in a little of flavor about how to analyze this up in different situations.